Welcome to the fifth video in this unit, Unit 2. This is a quadratic review and the overview of the box optimization problem. You can see a quadratic here. We have a parabola with a positive a value because it's the end behavior. It rises to the right, rises to the left. The general form of a quadratic equation is ax squared plus bx plus c, written here. The vertex form of a quadratic equation is written here. You'll note that the a and the a are the same in both equations. An x is still an x, but they have different values and different things that these general forms give. On vertex form, the h and the k is the actual vertex. And then you can see that this right here is a perfect square. So if you were asked to find the vertex in vertex form, it'd be pretty easy to find that. On the general form of an equation, this c value right here, 0c, is the y-intercept always. So that's something that you can get from general form that you can't from vertex. Also, remember that a parabola is symmetrical about an axis. This particular one is symmetric about the y, but it is always symmetric about something. This is called the axis of symmetry. So it's always going to be symmetrical about a line. The line doesn't always have to be an axis, however. So the axis of symmetry is always going to pass through the vertex and will be the line, in this particular instance, x equals h, or the h coordinate of the vertex. The axis of symmetry is that. And then the vertex is hk. And they use hk because it's still an xy coordinate on the parabola, but it is specific to the vertex. To find the vertex in general form, you can actually use a formula, and it would be real helpful if you know this. It's going to be negative b over 2a. The x-coordinate of a vertex in general form can be found by taking negative b divided by 2a, and then you've got it. Once you have that coordinate, you can plug it back into the function and find the y-coordinate. It takes a little more effort, but it is highly effective. So I want you to be sure that you write that down. The axis of symmetry in this particular case, I don't know why I'm writing h, would be x equals negative b over 2a. And that's for an equation written in general form. In vertex form, you can find that immediately. To find the y-intercept in vertex form, you would just let x be 0 and then solve for y. And so that would be the easiest way to find that. And of course, the axis of symmetry is just going to be x equals h. So it's important that you get this down. We're going to be using that also to find it, and sometimes it's just nice to have. Here's an example. This is a function, should be written as a function, f of x equals. This is a function that is written in general form, so instead of putting it in vertex form, I'm going to use this negative b over 2a to find the x and y coordinates of the vertex, which is what it's asking for. So I have a is equal to 3, b is negative 12, and c is negative 10. And so negative 12 is just 12 over 2 times a, which is this. So 12 over 6 is 2. So the x-coordinate of the vertex is 2. To find the y, I'm just going to look for f of 2. So I have 3 times 2 squared minus 12 times 2 minus 10. And I have, this is 4 times 3, which is 12, minus 24 minus 10. And then I have 12 minus 24, negative 12, so negative 22. 4, 12, yeah. And so that's my vertex. So it's not bad, it's mostly just computation. All right, I want you to do this next problem with me. And you're going to need a graphing calculator. So get one out, get it nearby, turn it on, go to y equals, clear out y1, do zoom 6 to put your graph back in standard form. If your plot is on, turn your plot off. Remember that you go to y equals and arrow up to plot 1 and then hit your button. But I want you to work this problem on the calculator with me because I don't have a calculator on the screen here. So some of this is going to be verbal, but all of that you should have been able to do. So stop the video, get your calculator ready to go, and then join me back again. The problem is here that we want to create a coverless box from a single sheet of cardboard that is 20 inches wide and 28 inches long by cutting squares of the same length out of the corners. So 4 equal squares, even though what I'm drawing doesn't show an equal square. And so what you would do is you would actually cut these out and fold up the sides so that this dotted thing is the bottom of the box. And the sides fold up, right? And it makes just a little folded box. And what we want to do is maximize the volume of this box. So remember that a box's volume is length times width times height. Now right now it's flat, it has no height. But what we're going to do is fold up the edges, and since all of these are squares and all the sides are the same, we're going to let the sides of each of these squares be x. Okay? So when I fold this up, it's going to look more like this, a three-dimensional box that doesn't have a lid. Okay? So it's open. This is open on the top, but it has a bottom. All right? So this is going to be the height. This is going to be the length, and this is going to be the width of the box after it's folded up. All right, so looking back at the laying out, we can tell that the height of this is going to be x. So the height will be x long. Now, the length of it, this right here, is what we're trying to look at for the length. So the length, if I went all the way across, would be 28, but I just want this piece right here. So 28 minus x minus x. So the length is going to be the total length minus 2x. The width is going to be this piece right here. Well, if I went all the way across, it'd be 20. So this is going to be the width is going to be 20 minus 2x. So to find the volume in terms of x, I would have length times width times height. So I'm going to have x times 28 minus 2x and 20 minus 2x. Now, it's at this point that I forgot the equal sign, all of these problems are the same to this point, all of them, because you have a box, and the only thing you can really change is the size of the paper. So if you have a 30 by 34, then it changes, then 28 becomes 34, and 20 becomes, the other number. So it's going to look like this every time. So length times width times height, and there you go. Do not take the time to multiply this out. Instead, put this function, x times 28, with the parentheses and everything, in y1. So go ahead and do that. Put that in y1. And you can stop because I'm going to keep talking here. And then what I want to do is maximize the volume. So in other words, this function is a third-degree polynomial, right? Odd function polynomial, which has a max and a min. So it's going to look something like this after we graph it. Right, so I don't want the min, I want the max. I want to maximize the volume. So what I'm looking for are the coordinates for this point. In order to graph it, however, you're going to have to mess with the window. And that took me a minute. But I'll give you a hint. I changed the x min to 0 and the x max to 30. And the reason I did that was because all the possible values for x are going to have to be somewhere between 0 and 28. Right? So I just added a couple and did that by scale 1. On the y min and max, I'm going to run out of room, but on the y min and max, I ended up having to go from negative 200 to about 1200, and then my scale was 100. And that seemed to work fine. And when you do that and graph it, you should get something that looks like this kind of graph. Go to second trace and max and look for the maximum point. You can use the right and left arrows, or you can actually plug in values. I plug in 0, hit enter, then 5, then enter again for guess, and got, for a coordinate, the answer was 3.8366. See if you get the same thing. And then 961.315. And that's awesome. Except, what the heck does that mean? Well, this first is x, right? So that is the height that's what size I need to cut my squares. Which, you know, try to cut it 3.83, because you'd have to do probably inches, right? So 3.83 inches, not quite 4. And that would give me a max volume, and that's what this is. A maximum volume of 961.315. And so that would be inches cubed. So what you would say is let me see if I can write it up here. The max volume is 961.32 inches cubed, because it's volume, if you cut squares that are 3.8366 inches on each side. And so that's describing. But the box problem is the same. Optimizing a box problem is just cutting the squares, putting that in there, graphing it, and finding a maximum. And you're finding the maximum point on a degree 3 polynomial. So we'll have more of these in class. This was a really long example, but this is the last one. So I will see you in class, and we will talk more about this then. See you then.